Heat transfer is made up, okay? Heat transfer is an invention. In particular, it takes a unique place in the physical sciences because as you start to learn more and more about how heat transfer works, why we model things in the study of heat transfer the way that we do, you start to see very clearly that there isn't necessarily some set of like fundamental understanding of how the universe works that gets baked into this. Okay? It really does feel like it's this kind of conceptual house of cards that we humans have built up, invented, right, made up, to try to see if we can't understand the universe around us. But there's nothing wrong with this sort of thing, right? In fact, all theories of physics are precisely this. It's an idea, it's something that we make up to try to understand and give names and concepts to the things that we see around us. Okay? But heat transfer takes kind of a unique place in the study of the physical sciences in the sense that it is both very, very ad hoc, which we'll start getting into once we actually start learning about the equations of heat transfer, but it is also uniquely useful, okay? Heat transfer is one of those things that allows us to put people on the moon. It allows people to survive, extraordinarily tough wintry climates or even desert climates. Every single building that you can think of has some kind of centralized HVAC system, and all of that is powered by an understanding that we've created of how heat, whatever that means, is transferred between different things. And so there's nothing wrong with heat transfer being just this invention because the wheel is also an invention, right? The idea of steam, engines is an invention. A rocket is an invention. And so even though we don't necessarily have a claim to an objective understanding of reality the way that physicists do, who cares, right? Who cares about understanding what the universe really is? What we do care about is about making sure that, people are able to survive in the winter, to create societal good by creating technology that allows us to exploit this very fundamental feature of reality and then utilize some patchwork framework of math to be able to jury-rig modern society, basically. And so what I plan to talk about, not just right now, but throughout the entirety of the semester, is to give you an understanding of, one, the vocabulary that we as engineers and physicists and even mathematicians use to describe what we consider to be heat transfer, right? What even is heat transfer? What's heat? Right? So we have to first start to develop a sense of what are the key concepts that allow us to generate some sort of understanding of what heat is and what heat transfer is. And then to be able to use those concepts in a way that actually lets us build devices, right? To understand how temperatures change. And that's kind of the point, right? So if we're going to operate under this claim that heat transfer is just this invention, we actually have to start thinking about, okay, well, why, right? Everything needs a purpose, especially when we're talking about inventions. If you reinvent the wheel, most people are just going to be like, well, what's the point? So what is the point? Okay, what motivates an individual to generate a theory of heat transfer in the first place? And although the answer might be a little bit simple, for the purposes of being coherent, let's start with that. So put yourself in the position of someone who existed, at the very beginning of history. We don't necessarily have, at the beginning of history, a culture of science. We don't even know what that word means. We are only humans living in a world that we are trying to understand in even the most basic senses. And one of the things that we notice is that if I go and take a rock, which I'm going to conveniently shape like a cube, right? So I find a suspiciously cube-shaped rock, and I put my hand on it, it feels funny, right? It feels warm. I come up with this word to describe the feeling of what this cube is. It feels warm. And then maybe I touch it some other time, maybe at night, and I touch it again, it feels different. It feels cold. And so what's happening is that I'm feeling this sort of property associated with this object that I have to come up with words for. And it seems like that property changes over time, right? So sometimes it's warm, sometimes it's cold. So it's not something that's a fundamental property of the rock, unlike maybe say it's, chemical composition or asperity or whatever. And so there's some kind of property, right? So I try to convince myself that I'm not crazy. I invite my friend Grug over and I say, hey Grug, listen, if I put my hand on this rock, it feels warm or cold. And Grug touches it, and whenever I say that it's warm, he says it's warm too. And whenever I say it's cold, he says it's cold too. And so we start to understand, oh wait, maybe this isn't just me, right? So it's not an emotion, it's not something subjective about my experience in the universe. It seems like this property of this rock is something I can share, right? Like whenever I feel it, he feels it. And so it turns out that this begins to create an understanding of like a fundamental material property, well, not material, but a fundamental property that an object can have that is objective in the sense that multiple people can perform a measurement and then say, oh yeah, this is actually, that we agree, okay? Which is the bedrock of science. And that property, right, is temperature. Now, there's a funny kind of backwards reason as to why it is that this actually works. And the reason that it works is because humans tend to be pretty good thermostats in the sense that we're all, at roughly speaking, somewhere on the order of about 98.6, maybe a degree or two Fahrenheit higher or lower. And what that winds up meaning is that, if my temperature had actually been a baseline temperature that's like 10 degrees Fahrenheit lower than my friend Grug's, then actually maybe I'd be feeling something that's cold instead of hot whenever they'd be feeling something that's the opposite. Okay, but the fact that most humans are operating at roughly the same operating temperature means that this idea of constructing a temperature works, right? So that we've actually honed in on something that makes sense. And you may ask yourself, well, what is temperature? Like, what is fundamentally temperature? So I've just given you a description from the perspective of what someone in the Neolithic would describe as being temperature, but like scientifically, what is it? And the answer is that it actually depends. So we won't get into it necessarily in this course, simply because of the fact that we actually, weirdly enough, don't care too much about what temperature is in the context of like, where does it come from? But you'll find that if you actually go and study statistical mechanics, you'll find that there are actually multiple different definitions of temperature. So this is not something that we're stepping in and saying, oh, we're going to ignore because it's too complex for us. We're ignoring because it's just sort of annoying to keep track of anything that isn't what directly affects us. Okay? So keep that in mind as we go through it. Where you can always imagine that there's some fundamental physical description of what's happening in these systems that we don't actually really care that much about. Because all we care about is the fact that when I touch this thing, Grug touches it too. We both detect the same temperature, or we both detect the same feeling, and therefore we interpret that as temperature. Okay? So this happens, all right? So we define this idea of temperature, and then we set that up as kind of the basic building block of our understanding of heat transfer. But really where heat transfer comes from is from an observation that happens after. So I create the notion of temperature, I get the Neolithic equivalent of the Nobel Prize for defining temperature, but then I notice something very interesting. If I take a rock, my friend Grug takes a rock, okay, and we put those rocks together, line them up side by side, and maybe this rock had some temperature T1. So maybe it felt warm. So I don't necessarily have like a thermometer, but I can use my hand and say that, well, okay, temperature 1 is warm. Okay, so this rock is warm. And this rock T2 that my friend Grug found is cold. Okay? And we take those two rocks and we put them together and we wait. And one of the things that we're going to observe is that no matter how warm or how cold these two rocks are, no matter what the rocks are made up of, they might be, obsidian or glass or clay or whatever, it doesn't matter what they're made up of, putting these two rocks together inevitably causes the temperature of both of these things to equilibrate, which I, as a prehistoric scientist, detect as basically touching both of the rocks and realizing, oh, actually, this is, they're both the same temperature, right? They both feel just as warm or just as cold. And so this is the fundamental observation of heat transfer, which is that temperatures over time equilibrate. Now this is very interesting, right? Because now the question is, well, how does it happen? How do I construct an idea of what's actually going on? But because, we're experimentalists and we like fiddling around with rocks, our priority isn't necessarily to start coming up with maths and invent the equations. What we want to do is to try to test out different scenarios involving my funny rocks to be able to try to see if we can't observe when this happens or when this doesn't happen, and to construct some understanding of what's going on here. Okay? So let's try to think about this from the perspective of a Neolithic science program. So let me write that down, make sure that we're all clear on this. So now I'm going to embark on a series of experiments, okay, to try to understand how this notion of temperature equilibrating takes place. What are the different mechanisms or ways that I can classify this thing occurring? All right, and so the first one, or at least the first experiment that I do, is what I described before, right? You take two rocks, different temperatures, place them together, and then you notice that the temperatures equilibrate. And somehow what that means is that there must have been a process, something that these rocks had that interacted with each other that caused those temperatures to equilibrate. Okay? Usually, the way that we try to understand this, or the way that we tried to understand this way back when, was with the notion of a caloric. So this is a little bit less Neolithic and more Middle Ages, but the whole idea was that we were really into invisible liquids back then. We loved the idea of everything being governed by fluids, right? So medicine, you used to say if you had problems with your liver or if you had a flu or whatever, you had an imbalance of humors, which were these funny little liquids that lived in your body. And, you know, and so that sort of natural philosophy led into this idea of something that's called a caloric. And the caloric was this idea that every object had this invisible liquid inside of it that governed its temperature. So if it had a lot of caloric, it would have a high temperature. If it had very little caloric, it would have a low temperature. And the whole point is that if you took two objects together, the caloric would kind of flow between the objects. We would never see it because it's invisible and imperceptible, but the whole idea is that this is essentially what would happen. Okay? So, and so the whole point is that me and the rest of my pals from the Neolithic Science program believe that there's this invisible liquid that is transferring temperature, so to speak, between object one and object two in the form of this caloric. Now, maybe I haven't invented a theory of caloric either way, but you can imagine that we think of temperature as flowing from one place to another. And so because I observed that this thing is happening in rocks, right? So I take any two rocks and I push them together and I keep observing this sort of behavior, I come up with this idea, okay? And I call this physical process, the process via which this temperature equilibration occurs between two solid objects, I call this conduction, okay? Or thermal conduction, if I want to be more precise. And the thing that distinguishes it, or the thing that we use, is that we perform this experiment and we see that it happens between or inside solid objects. So whatever this mechanism of transference is, it's happening between or inside solid objects, like these rocks. Okay? So I generate my experiment, everything goes great, wonderful. Now I say, well, is this the only way that temperatures equilibrate? Is there another way that I can try to see whether or not I can cause two rocks or two objects to have temperatures that eventually become the same? And the answer is yes. In fact, I can do that. And the way that that's going to happen, the experiment that we're going to construct, is we're actually going to say, well, maybe, just maybe, let's not even consider two rocks, right? So what happens if I now take one of those rocks and I dunk it inside of a pool of water, all right? And so maybe this pool of water is warmed up either because it's like a hot spring or there's some, you know, I invent fire and then warm it up. But the whole point is that I take some pool of water, I dunk my little rock in it, I make sure that my rock is cold and that the water is warm, okay? So now The rock has a temperature T1, and the water has a temperature T2. And what I start to observe when I actually take these things, when I make this happen, okay, is that eventually the temperature between these two things equilibrates as well. Okay? And although this seems like it's maybe kind of obvious to us in the modern day, it is fundamentally a different step, right? Because before, the whole notion of heat transfer that we were describing was something that occurred entirely between solid objects, right? We didn't really have experimental evidence that something that's a solid and something that's a fluid would be able to exchange heat too. In fact, that we can define a temperature for such a thing. And so what we do when we observe this, right, when we observe that this equilibration happens, it means that there has to have been some temperature equilibration process between these two things that feels, to my Neolithic mind, maybe different. Feels like it's different. Okay, we don't actually know because we haven't spent time describing what is actually happening, right? But we take a look at this thing and we say, well, now this is a new mechanism of temperature equilibration, which we're going to call convection. Okay? And the whole idea behind convection is that now it's representative of saying that it occurs between a fluid and another substance. Now, I'm saying another substance here only because of the fact that there is this possibility, right, that this is a solid, but also if you took like two immiscible liquids, like say water and oil, and you put them together, you'd observe the same exact sort of behavior, right? So even though these things aren't mixing, you'd find that actually the temperatures equilibrate, no matter what those initial temperatures are. Okay, eventually, given enough time, they will equilibrate. So great, so my Neolithic science program is going great. And then my friend Grug comes up with this great idea, all right? He says, well, something is common between conduction and convection, which is that there's always stuff, right? So there's this idea that, okay, yes, I have a rock or some water or some liquid, and that rock is transferring whatever this invisible substance is to this other substance, but there's always something in the middle. Okay, and that makes sense because it's very rare for us to find on Earth any place where there's nothing, right? We're usually always surrounded by air and by stuff, But he has this great idea. He says, well, I got my friend Glug to pump out, to create this rock-like dome made out of glass or whatever. Okay, so we made this little dome. Okay? And then me and my friend Glug pumped all the air out. We made some clever, simple mechanism, and we have the ability now to be able to pump all of this air out, such that there should be no air located inside of this thing. Right? And then I'm going to come up with a fancy word for that, and I'm going to call it vacuum. Okay? And so the idea is now to basically say, okay, well, if I took a rock with temperature T1, and I took a rock with temperature T2, and I put them in there, and I evacuated the chamber, okay, will these two things equilibrate? Will the temperature become eventually the same? And this is not a super obvious question because we don't know whether or not temperature equilibration happens in the absence of a medium, right? In the absence of matter. In order for these two things to equilibrate temperatures, there would have to be a mechanism via which this temperature equilibration occurs without there being matter, without there being anything that is transmitting the temperature from T1 to T2 or vice versa. And what it actually turns out is that when you do this experiment, you actually do see that the temperatures of these two things equilibrate. Not only do they equilibrate with each other, but they also equilibrate with the temperature of the dome that I'm using to vacuum out air. Right? So the temperature of all three of these things eventually, given enough time, becomes the exact same thing. And that mechanism, for reasons that will be explained in later videos, is called radiation. Okay? And the way that we define radiation at least based on these notions of experiments that we're creating, is that it occurs between objects without an intervening medium. Okay, so there's no air. There's no contact between these two things. Basically, whenever we observe that heat transfer occurs between two objects that are not, that there's no medium between them, there's no matter between them, then we call this thing radiation. And again, obviously you've probably heard the term radiation before. It probably feels like it's a little bit more Chernobyl than anything that has to do with heat transfer, but we'll see as we go along further and further into the courses and into these videos that there's actually good reason why this thing is called radiation. Okay? And so these are the three different modes of what we commonly refer to as heat transfer in the literature. And you might start thinking to yourself, if you haven't already, hold on a second, this doesn't feel like the smartest way to go about things. Because if we identify these three different modes of heat, of what we're eventually going to start calling heat transfer, as different things, then what happens if I, for example, go back to my little rock, to my original conduction rock experiment, okay? And if I take these two rocks and I put them together, we had said that conduction was the mechanism via which temperatures were equilibrating here, but why wouldn't there be radiation there too? Right? Like whatever physical mechanism is responsible for causing heat transfer to occur between these two things, what we're eventually going to call heat transfer, whatever physical mechanism should have been happening here, if it happens in the without the presence of the medium, then why wouldn't it happen with the medium, right? What happens, for example, if I have another experiment where I maybe take a rock and I slide it down a floor? Okay, so I have this rock and I slide it. So maybe I have a cold rock and I slide it down a warm floor. And this thing is transferring heat from, T1 to T2 or T2 to T1. The temperatures will eventually equilibrate like we expect. But this rock is moving. Does it count because it's moving as a solid or as a fluid? What if instead this was something that we couldn't really refer to as being either a solid or a fluid? What if this was maybe something like, I don't know, like some goop of tomato paste, right? Something that we couldn't really define as being either a solid or a fluid. And you can start to see that even though it seems like we had a pretty good idea in terms of creating this sort of Neolithic understanding of how heat transfer occurs, if we really start to think about scenarios, like really start digging into it, we'll start to find that the trichotomy of conduction, convection, and radiation isn't really something that holds up to a lot of scrutiny. Okay? It's still super useful. I'm not trying to be a conspiracy theorist here or anything, but the point is that our understanding of this comes from a very, very rudimentary position of thinking about what we're eventually going to call heat transfer as this sort of like simple experimentally testable thing. And as we go through the course, you're going to start asking yourself, well, hold on, this guy never answered the question of like, is there radiation happening whenever there's conduction? Does radiation happen all the time? What is heat transfer between these two surfaces, conduction or convection? And I'm not going to be able to answer those questions because those questions aren't really sensible, because the definitions that we have don't really accommodate for that, okay? And the whole point of telling you about all of this, rather than me just being an edgy contrarian, is to kind of tell you, like, we're building this up as we go. We're inventing all of this. There's no textbook or objective, figure of authority that is telling us, yes, conduction has to be this or convection has to be this, and this is the way the world works. We're just making this up as we go, okay? And you'll see that in the process of making these things up as we go, somehow we're going to come up with an understanding that's going to let us build, jet engines and HVAC systems and all sorts of things, all right? So that is it for today. What we are going to be talking about in the next lecture is simply going to be on how to actually create an understanding of the physical quantities that we're going to use to describe heat transfer, right? So we have some idea of mechanisms that we could describe, but naming mechanisms isn't super useful, right? We actually have to come up with some kind of math, some sort of objective understanding of how these things actually occur. So that's what we're going to do in the next lecture. All right, see y'all.